Our society is facing one of the major challenges right now is to produce more food for a growing population.
How can we produce more in less polluting or having less impact on the environment that is socially just but also economically profitable for the farmers?
One of these challenges is insect pest damage, and globally around 30% of insect yield is damaged by insect pests.
As scientists, we need to address the 4 pillars of sustainability. That is environmental, social, human, and economic. We can achieve this by developing methods of crop protection that are both sustainable and economically viable to enable us to realise the yield potential of our crops. But crop protection isn't new. For example, at least 2,000 years ago in ancient China, people used a form of chemical crop protection by treating their crops with chrysanthemum extracts. These extracts contain pyrothrins, from which our modern-day pyrethroids have been developed. Another good example of crop protection practices from around a similar time is the use of yellow citrus ants to control insect pests in citrus orchards, and this was probably the first documented example of biological control.
The use of biological controls to control pest insect populations is still important today and is becoming increasingly popular as a more sustainable alternative to chemical pesticides. Examples of current biological control agents include natural enemies such as ladybirds and predatory bugs, as well as other arthropods such as predatory mites and spiders.
Unfortunately, the use of biological controls isn't always enough to manage an insect pest population. An infestation being a good example of this, and in these cases it becomes necessary to use pesticides. Our approach in EcoStack is to identify prospective biologics within the venoms of parasitic wasps or spiders to develop novel biopesticides. These could be used as part of integrated pest management strategies in place of the more environmentally damaging alternatives. Therefore, rather than using the whole organism itself as a biological control agent, our aim is to use their molecules and related genes to enhance current crop protection strategies.
While some natural insect enemies use their prey as a food source, the parasitic wasp lays eggs within a host insect. The wasp simultaneously injects venom containing viruses and compounds which suppress the host's immune defences, allowing the parasitoid egg to develop. We have identified several promising proteins in the venoms of parasitic wasps and spiders which could be developed into biopesticides. We are expressing their encoding genes in well-established expression systems, such as Pichia pastoris, that are successfully used to produce pharmaceuticals such as insulin and food processes such as baking and brewing. This means that we can produce large quantities of these compounds for their development as biopesticides. We have partnered with industry leaders such as the Centre for Process Innovation, CPI, which is a national industrial biotechnology facility. This partnership has enabled us to produce large quantities of these insecticidal compounds for formulation in a cost-effective, more environmentally friendly way. Once we have produced the biopesticide, we then test its effectiveness against a range of agriculturally important pest insects. These represent both chewing and sap-sucking pest insects. Initially, we test the compounds by microinjection. Firstly, a needle is pulled using glass tubes. The candidate biopesticide is taken up into a nano-injector and then injected into the target insect. The insect will then be monitored under controlled conditions to verify toxicity. We also test the promising candidates using artificial diet systems. This involves the preparation of artificial solid or liquid diets with the candidate biopesticide. The target insect is then introduced to the diet. They are then monitored under controlled conditions and finally assessed for the candidate biopesticide's toxicity. However, before a product can be marketed, it is essential to demonstrate that it is safe to use. We therefore carry out biosafety studies, not only on non-target organisms, but importantly, on those that provide essential ecosystem services, such as pollinators. We also carry out biosafety studies on other insects that are still used as biological control agents, such as spiders and parasitic wasps.
The idea behind EcoStack is to combine, in other words stack, different insect pest control strategies. So currently, we're developing several novel biopesticides which target either the central nervous system of the pest insect or its immune system. And these biopesticides have been informed to a large extent from biological control agents themselves. By stacking our novel biopesticides with well-established biological control agents, we have shown that they enhance the effectiveness of entomopathogens such as Bavaria and Bacillus thuringiensis, commonly known as BT. This approach of stacking different control strategies is currently looking very promising indeed. One of the molecules we're working on has been isolated from the venom of spiders and is used by the spider to paralyze its prey. This particular compound targets the sodium ion channels of the insect's central nervous system. Incidentally, this is the same target as pyrethroid insecticides, but has the advantage of being more specific and therefore a more environmentally sustainable alternative.